Self-driving cars, delivery drones, and fleets of automated mining machines have moved from headlines to habits, but they can only travel as fast as the tech underneath it. On Interconnected, a new show by Equinix that explores the hidden infrastructure behind our connected future, they shed light on the challenges of scaling safety, where computation happens, and a future where cities are built with autonomy in mind. MIT research scientist Brian Reimer and emerging technology leader Patrina Steele explain how the way we move is changing and where the future will take us. Listen on Spotify or wherever you get your podcasts.
Cloudcast Media presents from the massive studios in Raleigh, North Carolina. This is the Cloudcast with Aaron Delp and Brian Gracely, bringing you the best of cloud computing from around the world.
Good morning, good evening, wherever you are, and welcome back to the Cloudcast. We're coming to you live from our massive Cloudcast studios here in Raleigh, North Carolina. For all of our listeners in the United States, it is almost Thanksgiving, and we're very thankful to everyone out there. Thank you for taking the time to listen to the show. Thank you for supporting us over the years, and thank you for being a part of the community. It's hard to believe we're closing in on 15 years and 1,000 shows. Of course, this wouldn't be possible without your support. For this week's show, we have a long-time returning guest. Evan Kaplan from Influx Data joins us, and today we're going to be talking about time series databases and the use cases for AI. And that is coming up right after this break.
Today's show is brought to you by TestCube. Testing applications in Kubernetes doesn't have to be complicated. TestCube is your go-to platform for cloud-native continuous testing. With TestCube, you can orchestrate, scale, and automate tests effortlessly right within Kubernetes, catching issues early and deploying with confidence. Try it out today and see why engineering teams trust TestCube to keep their testing simple and scalable. Your test, your tools, your infrastructure, finally together. Check it out at testcube.io/cloudcast. Today's show is sponsored by Mailtrap, modern email delivery for developers. The complete email API that does everything you need it to do. Try it today at mailtrap.io and get 20% off for all plans with the promo code CLOUDCAST. That's mailtrap.io, mailtrap.io.
And we're back, and we have a really interesting AI-themed topic this week. We've been talking about AI a lot on this show, but I think almost maybe over-rotated slightly, if you will, of what is GenAI and LLMs, and that's what we've been talking about because that's been the big rage for quite some time. And we're actually going to be talking about a different portion of AI this week. And for that discussion, we have Evan Kaplan, CEO at Influx Data. How are you doing, Evan?
Good, I'm doing great. Aaron, thanks for having me.
Absolutely. And so first of all, welcome back to the show. Not everyone is going to know, but link is in the show notes. You were actually on the podcast the last time back in, I believe, 2019 on the Cloudcast number 394. And we were talking about time series databases and just an introduction to time series in general. And that's our topic for today is time series and time series specifically for AI. So give everyone a quick introduction, if you don't mind, and then we'll kind of start to dig into our topic for today, Evan.
Sure. First of all, congratulations to you. If it was 2019 and I was episode 300 something, and now you're approaching episode 1000, you're sort of an Iron Man in the podcast world.
Well, thank you. Thank you for that.
To get to 300 by 2019 would have made you a bit of an Iron Man. So thanks for your interest. I think, I'll rehearse the background a little bit. I'm the CEO of Influx Data. I have a long history of leadership in tech companies, starting with my own company, started out of my house, running a public company, and then this is my third real CEO gig. But we're approaching, almost 30 years of being a CEO of tech companies, and almost all of them infrastructure, and almost all of them deeply technical products, which is where my interest lies. I joined Influx a little over 9 years ago. And I was at a seat at Trinity Ventures looking at deals with them and being an executive in residence. And met Paul Dix, the founder. And we hit it off. And I really liked the space. I felt a lot of conviction about open source. Having run a public company, done large open source projects, I was pretty bullish on open source and infrastructure. I felt really strongly about this thing called time series. It looked like a bit of a backwater, but to me was going to be increasingly relevant. And this was certainly before I conceptualized stuff around AI or really understood things beyond basic machine learning. But still, the time series thing I thought was really interesting for financial and scientific, but then it would break out much more into the mainstream, which has turned out to be true. And, we're now 9 years into this journey. We have about 2,600 commercial customers, but we have about 1.3 million users or sites that run Influx every single day, from people at home to the very, very largest of corporations that you can name. And so it's been a gratifying business, and I feel like we're just at the beginning of this very next phase, which is, the stuff that you're highlighting here, which is the physical AI world. So that's just the background. Anything else I can do to fill in the background?
No, that is absolutely perfect, and I love the thinking behind time series and kind of time series, because we're going to definitely talk about that here in just a second. But the whole idea of like the relevancy of it going forward, because the one thing I can say, in the last couple of years since we spoke is yeah, absolutely. As you're seeing more and more things like, I don't know, autonomous driving or, space travel or all of these other things that just benefit from this both real-time logging as well as as fast as possible processing of all of this data and getting insights into it. So for those that maybe aren't up to speed on that, give everyone kind of a quick definition of if you will, of like, okay, when you say time series, what do you think that is and the impact in recent years for that?
Yeah, it's a very specific definition. It's metrics and events at scale, both. So events being things that are happening in the world, and metrics are things you're pulling to in the world. But think about it as telemetry writ broadly. If you know that what you're collecting can best be indexed based on time, right, and is almost always best indexed, you can be super efficient. You can be super efficient at pulling queries and making queries super fast, in some cases sub 5-10 millisecond, which is pretty amazing. You can be super efficient at ingesting data at high volume, billions of points per second, because you already know what the basic format's going to be and how to pull it in and how to store it and how to be able to read it and write it. You can be efficient at the dynamics, which include things like downsampling data, so collecting high-resolution data for short periods of time and then summarizing that data on a continuous basis. You can be super efficient about the storage of that data so that you can collect the most amount of telemetry in the least. That's the basic principle behind time series. Our platform is schema on write, so you don't have to know everything you need to know before you start. You can start collecting data and then organizing it a little bit better as you go, so you have more flexibility. The platform handles backfill because some data comes later than others. If you have disconnected networks or things like that and sensors aren't available, you have to be able to backfill the data efficiently. And so you start looking at that problem space and you think to yourself, you can do this with a general purpose database like a Postgres or an Oracle or MySQL, but you have to build a whole lot of stuff on top of it, and it's never quite performant. And so if you want a system, we'll go into this a little bit as you ask other questions. If you want a system that is responsive in real time, that is capable of adapting and learning, you simply can't do it on a ad hoc, batch-oriented query process. You have to really be able to operate in near real time with the data. And so you build a platform that does that. And so we've consistently, we're the leader in the space by a pretty wide margin if you look at most of the indexes and the revenue and that sort of stuff. But I think it's just beginning. Yeah. Anyway, I hope that's a good background about the technology.
No, that's absolutely perfect. And then I'm kind of putting two pieces together, if you will. There's the time series piece, and the other one is the AI piece. And the reason why I want to cover this at a foundational level is, like I said, most of the listeners here, they're going to be familiar with AI, but they're going to immediately equate AI with LLMs and generative AI and agentic AI. But what we're talking about here is much more practical. Like, and I've seen it referred to as physical AI, meaning, think of it as like robotics or autonomous driving or some of these things. It's basically AI meets the real world, right? And so let's talk about that very quickly as well, because there's this concept of deterministic AI versus probabilistic AI solutions. And so tell everyone a little bit about the difference and why that matters, Evan.
Thank you. It's a really good question, and it's formed well, and it's relatively easy to conceptualize around. But let's start with the highest level is LLMs are ferociously powerful. I'm continue to be amazed at my own use of ChatGPT, the dynamics that happen there, a level of intelligence that doesn't seem like it could logically appear from whatever input I'm making in. And so I stand in awe of some of the advancements over the last few years, particularly, with LLMs. But if you look at the LLM world, the space of data it has available is getting smaller and smaller because it's basically most of these LLMs have crawled what's equivalent to the Library of Congress and probably do something like that every month, right? We're just consuming all the written data in the history of what's available, and that's now available in the LLMs, and that computing power is pretty impressive. And in fact, if you listen to the folks who run these companies, they talk about the need for more synthetic data, to create more data, to basically run these LLMs, to create more language-oriented digital data, to create more images, that sort of stuff. And so their space is going to be fueled, and intelligence is going to be gained by creating more data. Now, that's the digital space. If you take the space of the physical world, you have an infinite amount of data that's available. Right? It's an infinite amount of data. Anything that moves, motion, operates, right? It's infinite, whether, this planet, multi-planet, whatever. It's just, anytime you talk about the physical world, that space is infinite. It's only a question of, at what resolution do you want to capture that picture? How much data can you handle? Now, clearly, the more data you can handle, the better you can build your models, the more accurate, and what you're referring to, the more deterministic. Because in the physical world, you can't afford probabilistic. I can't afford the self-driving car to say I probably won't hit that old lady walking across the street. I need to have like 29's assurance that that's not going to happen. And so when you instrument the physical world, the amount of data that's available to you is infinite, as opposed to the digital world. And now it's a matter of how you collect it efficiently and work to process it. And that's the view of where we feel like we fit in the physical world, is that we're going to see a requirement for consumption of more and more and more data. And I don't want to keep talking, but I can take you to the next level of that discussion if you want.
Yeah, no, I think that's fantastic. If you don't mind, please do that. And I had a kind of a follow-up question. I'll just ask it now because I think it goes to the same place. Is you had this analogy in an article you wrote actually about space, and the analogy in there was the data collection. You have this idea of like low resolution and high resolution, and the difference between, okay, yes, you can map something, but it might be a low-res picture or a high-res picture, and the differences in the details matter, like just where you were going with that. So if you don't mind, please elaborate.
Yeah, so thanks. That's actually a good feed and allows me to bridge to the next point. Is, if you want a system that's deterministic, you want to have higher and higher resolution, a higher and higher resolution picture to operate on it. And so, you start with the example of a satellite in space. If I need to know exactly where it needs to be, what coordinates it needs to sit in order to be in relationship to the other 1,000 low Earth orbit satellites there, in relation to the particular beam forming on back on Earth and what area coverage. Like I need to be very, 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 very deterministic, and so I need a very good picture. I need to know exactly what's going on at all points. I need to see all cases of what could go on, the solar flare or whatever. Like, I need to see the picture of that thing operating better and better if I'm going to apply intelligence to it. And so that resolution is what matters. The better the resolution, the more deterministic the outcome, almost always. I'm sure there are some exceptions, but the better the resolution, the more deterministic. Let's put it, if we put it on the ground here in just this self-autonomous vehicle or robotic sorts of things, the more I can see the picture of the real world that the car is operating in, and the more the telemetry I have about the car, the better system I can build about that interaction between them. And so the core to all intelligence is this repetitive learning cycle, which is I collect a set of data, right? I instrument something so I can collect a set of data. Think of it as eyes, nose, ears, whatever. I collect that set of data, right? And then I operate in the world with the conceptual thing about the way that's working. And of course it fails. And so I re-instrument, I collect, and of course it fails. I re-instrument and collect, and of course it fails. And if I do that 1 billion times, I have a self-driving car. If I do that 500,000 times at my house, I might have a robot that could fold laundry and not kill the dog while it's trying to do it, or whatever the metaphor you want to use, right? And so if you think about this cycle, there's almost a cybernetic loop of learning. The more I learn, the more resolution I have, the better I train the model. The better I train the model, the more resolution I get it. And think as I go forward, and that's intelligence. Now, I want the robot, I want the car, I want the satellite, I want it to operate in real time. And so it has to be able to adjust. It doesn't just need resolution, it has to be able to adjust to what it sees. So when the robot sees the dog, it has to be able to respond to that, right? And so it has to have that picture, that picture of the real world. That operating in real time, tied to the intelligence model, is what gets you, an autonomous system. And all these systems want to be autonomous. They don't all need to be, but they want to be. We want everything in our, want the dishwasher. Ideally, we want the dishwasher to know when it's full, and we want it to know when it's empty, and ideally even empty itself, right? Like this is the journey to removing entropy from our world. Like we just want that all over the place. We don't need it all over the place. It's probably not good that it's all over the place, but in general, we want systems that are self-healing, they're adaptive, and can operate in real time. So sorry for the super long answer.
No, I love it. But my infrastructure background, I immediately go to, I completely understand, low resolution, high resolution being better. But then I immediately go to, but then what happens, like at some point, there's always this tipping point of, okay, this is good enough. And then anything more might be, I don't know, it generates more noise and takes longer to process, or it becomes expensive to, process, or it becomes expensive to store. And so how do you determine what's the sweet spot where like high res is good enough versus say ultra high res, or like, how do you determine from where's the give and take?
You have an infrastructure background, right?
Yeah.
So I'd ask you the question: how many nines is good enough for what system? Right.
It depends on the business, right? Absolutely.
Right? And so, lots of systems. You run in a SaaS service that has an application. People will say 3 nines. But if you've got a self-driving car that's on the road doing all those people, 3 nines would not work. That means I'm going to hit one person every 30 days, whatever the metric is, right? So it really, it's not really our call. Our call is to build the thing that allows you to go as many nines as you need to go to make your system work. I think that's the right way to think about it, and I know it's the way you would think about it as an infrastructure engineer.
Absolutely.
Like, I know, boss, you want this thing never to fail, but 20 nines is going to cost you, 50x what 5 nines is going to cost you.
Yes, absolutely. Yeah, you look at I don't know if you had followed it, but AWS had a big outage a couple weeks ago, right? And everyone is like, well, hey, you can build in the redundancy, and don't go in the east or one region, but some people just don't because it's just too expensive, quite frankly. And they kind of take the hit, right? And so that's a prime example.
I started my career in aerospace, right? And all of those models, you're not even talking about, you're really not, you're almost talking about an infinite number of nines because the cost of a plane falling out of the sky is so dramatic that, and yet they do. And yet they do. But that, I mean, that's the model that I have in my head is you dial the nines and use the data that you want.
Yes. Yes. That makes perfect sense. Now, let me ask you this. I feel like, we have all this data. And we've always had all this data. Like you have these, just extensive collections of data, and sometimes it's in one or more databases. Sometimes it's in a data lake. There's all these kinds of, I'll call the term passive places you can store the data, right? And it's just kind of waiting there for someone to, hey, if you want to find the needles in the haystack, go ahead, right? But you have to go do it, and it's very manually to get those insights, and so. Through this and through AI and physical AI, are we starting to then shift into a less reactive and more proactive state with this, active intelligence and active use of data going forward? Is that something you're starting to see as this kind of intersection happens?
Well, you have as much experience as I do. You know how much data is stranded in enterprise silos and how much is not available for real intelligence processing, business information, whatever. It's just the nature of, what's been built over the years. There's 40-year-old data in Oracle. There's probably 50-year-old data in mainframes. There's probably, and that was the whole big data revolution. We'd throw them all into Hadoop and we'd somehow make sense of it. And intuitively, that sounds right. I think the same is true in the lake house, right? I do actually think, I think the lake houses are the next generation of the databases. The Databricks and the Snowflakes of the world are the Oracles and IBMs of when we started our career. And so I think there's, the silo stuff continues to be a problem, but it feels like it's getting better. And then the tool set, right? So, how to find the data with the models, right? How to govern the data. I think that's getting to a level of sophistication that didn't exist before. And so when you think about building these models, you have to pull structured data like influx, like all the time series data. You want to marry that potentially to business data if you're making certain kinds of decisions. You want to marry. I think a lot of that stuff happens in the lakehouse. I think the lakehouses are ideally fit for that. They're terrible at anything that has to be real time, right? They're terrible at building an operational platform, but they're fantastic, at least relatively over time, fantastic at building a place where you can build your models, do your work, think of it as your workbench, transform your data, do all that sort of stuff. But using them as an operational data would be a fool's errand, or maybe you just don't need that. You just don't need something that's truly operational. Maybe you can live with, 2-second queries for just a different kind of thing.
Yeah, that makes perfect sense. And kind of a last area I wanted to talk about a little bit as well was this whole idea of, okay, I really like that analogy of, okay, let's just take the autonomous driving because I think it's easy for everyone to picture. Okay, you have a lot of sensors, you have a lot of data, decisions need to be made very, very quickly. But where and how does that processing have to happen? Like, where does it need to be placed? And what I mean by that is, in that autonomous driving example, most of both sensors and decisions happen in vehicle. But there's other times where it's, say nearby, right? And as close as possible. And so you have this idea of like, does the processing source, is it simply just a matter of what's the latency allowed for the application, or is there other things to consider other than, speed of light and basic physics when it comes to, processing and where you put the processing when it comes to, time series?
Yeah, I think I'm not an expert in this. Obviously, I'm close enough to see some stuff. Clearly, if you have a self-driving car, you're not going to go for a cloud query to figure out what to do. You really, the latency ends up being really important. And essentially, you have to have an operational time series on board. You have to have something that already has the intelligence, the algorithms built in. And so those reactions are, sub-millisecond reactions, because that's what's at stake. right? As you get systems that are less requirement for that sort of stuff, potentially you could have efficient cloud-based resources that drive that. We have all sorts. Lots of our customers are 3-tier customers. They have influx at the edge or embedded, and then they have a cloud instance also where they back, and then lots of them are straight to the cloud. It really is latency is the single factor, right? Yeah. If you can live with 2 second, 1 second, 1.5 second latency for whatever system you're building, then you have some more flexibility. So.
Yeah, that makes sense. And this goes to a customer conversation I actually had. It would have been last Friday. There was an AI event up in New York City, and I was actually talking with somebody in the financial services industry, and we were just kind of chatting on like how do you measure this and how do you think about this, and it was really interesting. They said, look, at the end of the day, there's 2 basic things I care about: latency to the application, because that's what the end user is going to care about. And then cost to generate it. So in this instance, it was LLM. So it'd be like cost per token. But at the end of the day, like cost per unit, right? So like I have cost per unit on an operation side, and I have latency to the user or to the application that is required. And those are the only 2 parameters that ultimately matter. But with those 2, I can cost something and I can figure out how fast it is.
Yeah, latency is the other, the other side of the noise example. You can get a maximum latency. You can build. You can build out at the edge, very, very close to the edge on the device, but everything costs something. So what does your system need? But the point that I would make is that we live in the world of physical AI, where we have autonomous things operating in the world. Those systems need operational level latency. They cannot deal with, you cannot stop a factory robot from, putting in a bolt because it has to make a special query for an exception. It needs to have that information there, and that latency and that intelligence has to be acted on then, in real time. And so lots of people, real time is the buzzword these days. It's all real time. By the way, probably through both of our careers, it's been real time the whole time. Real time is different now, right? Autonomous physical systems, real time is different, just different. This isn't like, my user has to wait another second to see the screen refresh. This is like, I'm going to run over my cat.
Right. Completely.
The nicest example.
Yes, agreed. Well, Evan, I feel like that's a fantastic place to close this out. If anyone out there is interested, what's the best way for them to get started?
With us, if they're interested in playing with this, a lot of people start at home. They instrument things in their house. They build these small systems, which we always are supportive. We have a home version. The open source is clearly available. It's promiscuously licensed. And then if they build something that they really want to have production ready we have a commercial product that adds a lot of capability. And so you just go to www.influxdata.com. That sounds like a commercial. You go to our website or tap ChatGPT. I'm sure using the ChatGPT, and you'll find us. And it's pretty easy to get started, is what I'd say to your developer audience. It's surprisingly easy.
Fantastic. I love it.
Yeah.
Well, Evan, I thank you very much for your time today, and thank you for you being a returning guest after a couple of years as well.
I'll see you. This would put us I'll have to see you at episode 1600 now.
That's right. Absolutely. We'll book it right now. There you go. All right. Well, Evan, thank you very much for your time. And for everyone out there that's listening, thank you very much for your time as well. If you enjoy the podcast, wherever you get your podcast, if you can leave us a review, we would certainly appreciate it, and tell a friend. And we're always looking for feedback and additional shows and guest ideas as well. And it's show@thecloudcast.net. On behalf of Brian and myself, Brian wasn't able to make it this week, but we certainly appreciate everyone listening, and we will talk to everyone next week.
Thank you for listening to The Cloudcast. Please visit thecloudcast.net to find more shows, show notes, videos, and everything social media.